Okay, let's talk about special relativity and the twin paradox, in quotes. To really understand the twin paradox and how to calculate how much time the traveling twin experiences versus the fixed twin, you just need to understand two principles. One, we all travel through space-time at the speed of light. And that can be articulated by the equation your time squared plus your distance squared equals the speed of light squared. And sometimes this is said that we travel through time at the speed of light, which is true. So if you're in a fixed frame of reference, d goes to 0 because you don't travel any distance from your perspective, from your frame of reference. So your time squared equals the speed of light squared. So you're traveling through time at the speed of light, okay? Which is interesting because it's in meters per second, okay? Now, the second principle is which is derived from this first principle. The amount of space-time between any two space-time points, or the same is equal no matter what the space-time path is. Okay, so if you have two entities that are present at the same two space-time points, travel through the same total space-time. Now, the difference is one may have passed through more space and less time, and the other one will have traveled through less space but more time. I'm going to add a third one right here, and then the shortest distance, space distance, okay, spatial distance only. So this is d between two space-time points is the distance traveled in a single reference frame. That's the straight line. So consequently, the longest time between two space-time points is within a single reference frame. Okay, let's show this diagrammatically. Oh well. So this is a space-time line. So this is the time. And this is distance. Okay. All right. If you're in the same space, so let's take two space-time points in the same reference frame. That means they don't move any distance in terms of that reference frame. So it starts at 0 and ends up here. So these are two space-time points. And because you don't move any distance, this is a single frame of reference. You're just traveling down time at the speed of light. Now let's just say you travel 2 seconds and then another second, 2 seconds. So for path A, we'll call this path A between these two. Okay, path A. For path A, space-time path A equals 4 light seconds. okay? And so if it equals the time is, okay, path A, 4 light seconds time, okay. All right, and the distance is 0. So we have t squared plus d squared equals 4 squared plus 0 squared equals 16. Okay, 16, whatever. It's really just 4, but the t squared plus d squared is 16. Okay. Path B is the rocket ship path, and we'll do 0.5 of the speed of light. So he'll go out a distance of 1 light second and then return at another light second. Now this could be someone traveling and accelerating and decelerating. Obviously it's impossible in reality to do that, but or it could be one object traveling at half the speed of light in this direction, 0.5 c, 0.5 c, and then another object crossing its path and exchanging a timestamp at that point and returning. And then by calculating, summing up the clocks, you'll get the total time expired. Now, just here, you can see that the path B traveled 1 light second in this direction, and then another light second on the return, for a total of 2 light seconds of distance. So plugging that into the equation, we get t path B, so this is path A, t path B squared plus dB squared equals c squared. It doesn't actually equal c squared. It equals the distance between these two, okay? All right. In space-time, okay? Basically, it's going to equal TA squared plus dA squared. Well, this is 0. So we have, and this is what we're solving for. So we have 2 light seconds squared equals 4 light seconds squared, and TB2. Okay. Now we just solve for that. Very simple. TB squared equals the square root. Okay, it's TB equals the square root of 16 minus 4 equals square root of 12 equals 3.46. Okay, so light seconds. So so this so the time experienced by traveler B is equals to 3.4 light seconds, while the time for traveler A is 4 seconds. So this is your time dilation, and it's due to the fact that the total space-time is 4 seconds, but this one of them traveled 2 light seconds in distance it's an orthogonal path. So you use geometric addition, to calculate it all up. And it turns out you get 3.4 seconds. So let's check this. All right, let's check this using Lorentz's equation. Well, the Lorentz calculation for time dilation is 1 minus v squared over c squared. So t dilation equals 1 minus, so v, in this case, v velocity was 0.5 c. So you just get 1 over 1 minus 0.5 squared. 1 minus 0.25 square root of 0.75 equals 0.866. 3.46 seconds over 4 seconds approximately equals 0.866. So the exact same time dilation calculated just geometrically. And that's it. So you understand that between any 2 points, the total, if any path between the two same space-time points has the same total space-time distance. If you travel further in time, you travel less distance. The amount of the path with the least physical distance, spatial distance, is the path within the same space-time frame. And so if you travel more distance, you travel less time. Okay. Let's see here. Let's pull this one back and make a couple quick observations. One is that if you traveled at the speed of light, you would have traveled 2 seconds out and 2 seconds back. And so the distance you traveled would be equal to the time that the single reference frame traveler passed. And that means that you would have had zero time. Zero time would have passed if you traveled at the speed of light. And that just means that light doesn't experience time, which is a very interesting concept. And it's very important. The second thing is that, this path could be any path. It could travel all over the place, crazy. And all you need to do is add up the total distance traveled and then plug that into the equation. So it makes it very simple to calculate the time dilation for a non-constant speed. The other thing is it's not the acceleration. The reason why you need acceleration, or acceleration is often involved, is in order to travel a longer path, you have to have 2 reference frames to create something other than a straight line. And so the acceleration just allows you, so at this point would be the acceleration point, to have 2 reference frames. But 2 reference frames will always travel a longer spatial path and therefore have less time. So it's really about the number of reference frames you're in and how long you're in those reference frames, not the acceleration itself. And this is shown, like, if we had made this much longer, let's say we made this 4 seconds and 4 seconds, okay? And then you traveled further like this and this, you'd still have that same turnaround acceleration, same exact amount of acceleration and duration, but your time dilation would be much larger. But this is because your path, the total path is longer. The total spatial path is longer between the two, making it necessary to have a greater difference in time. Again, but the acceleration is the same, so the acceleration is not causing the time dilation. That's it. So that's an easy way to understand the real reason behind the so-called twin paradox, and that is not caused by acceleration. It's just caused by a longer spatial path, which then requires there to have been less time expired in order that the total space-time between 2 points is equal. That's it. Thanks.